The last type of problem that we want to look at in this module is what's called an inventory problem. So in this case, we have a company that is producing DVDs. Costs the company 40 cents to store a DVD for a year. Each time it has to make additional DVDs, it costs $250 to set up the equipment. So the question is, how do we best conserve our money? How do we reduce our costs by producing DVDs multiple times a year, once a year, produce all 20,000 in one shot? So there's the setup cost every time that we produce a new batch, and there's a storage cost for any product that we can't move immediately. So how do we minimize our cost? By minimizing both the cost of setup and production and the cost of storage. So let's set up two different variables here. Let's let X be the number of DVDs produced, and we'll let Y equal the number of production runs. So setup costs for the year will equal the $250 times Y, times every time we make a new production run. Storage costs are a little bit trickier to figure out. There's a good write-up in the e-text about how they come up with this, but basically we're averaging the amount that we're storing at any given time. So whatever our interval is for, the time interval is for storage, that number is decreasing from X, however many DVDs we're storing at one point, to 0 when we get down to a minimum. So if we average X and 0, that's X plus 0 divided by 2, or X over 2. So at any given point in time, we have, on average, X over 2 DVDs in storage. So our total cost is going to be equal to our setup cost plus our storage cost. Our setup cost is 250 times Y. Our storage cost is going to be 40 cents per DVD, so we have 0.4 times the number of DVDs in storage at a given time, which is going to be X over 2. So that'll be 250Y plus 0.2X is our cost equation that we want to minimize. Now the other problem here is that we have an equation in two variables. We don't want an equation in two variables because we haven't gotten to multivariable stuff. We will encounter that later this semester. So what we need to do is establish some relationship between X and Y so that we can rewrite this function in terms of just a single variable. So the relationship between X and Y, we have X DVDs that are going to be produced in each of Y production runs. So if we have 10 DVDs being produced in each production run, 2 production runs, 10 times 2 would be 20 total DVDs being produced. So however many DVDs we produce in each run times the number of runs gives us our total DVDs produced, and in this case we need to meet a demand of 20,000 DVDs. So solving this for Y, we get Y equals 20,000 over X. So we'll be able to use this to rewrite our cost function. And the other thing that we need is a domain for X. So we're going to produce at least one DVD in each production run. So if we have one DVD being produced in each production run, we would need 20,000 production runs, which doesn't make a lot of sense, versus our maximum number of DVDs produced in each production run could be 20,000. So meaning we do one production run, and in that production run we produce all 20,000 DVDs. So the problem that we're interested in this case is minimizing the cost, C of X, of 250 times 20,000 over x. So replacing this original cost equation, replacing that value y with 20,000 over x, plus 0.2x on the interval from 1 to 20,000. So we can simplify this a little bit. This is 5 million over x plus 0.2x. So now we proceed in the same way as before. We'll find any critical values. So we'll take the derivative of our cost function, which will be negative 5 million over x squared plus 0.2. So we take our derivative, set it equal to 0, which is going to give us x squared equals 5 million over 0.2, which is 25,000. So we have x squared equals 25 million. And then if we take the square root of both sides, this will give us x equals plus or minus 5,000. So really, we don't need to worry about the negative 5,000 since that's outside our domain, because we're not going to produce negative number of DVDs. So the only critical value we have to worry about is 5,000. But let's put that other value off to the side. And we'll just cross that one out since it's outside our domain. So we have a single value to consider. We'll take the second derivative, which will be 10 million over x cubed. And we'll evaluate that at negative 5,000. Or I'm sorry, positive 5,000. Negative 5,000 is what we threw out. And the nice thing here is we don't even have to figure out what this result would be. We just have to determine if we can say that it's positive or negative. In this case, a positive divided by a positive is going to be a positive. So that's greater than 0, meaning that C of 5,000 is an absolute maximum. So if we go back to that expression that we have for relating y and x, y equals 20,000 over x, which implies y equals 20,000 divided by 5,000, since that's where our absolute, I'm sorry, I think I said max before, absolute minimum. So 20,000 divided by 5,000 is going to give us 4. So when x is 5,000, y is 4, meaning that we have our minimum cost occurs when 5,000 DVDs are produced four times a year. So the most efficient, cheapest way to meet this demand of DVDs that we need to produce is to complete 4 different production runs throughout the year, and with each production run, we'll print another 5,000 DVDs.